In question number 1, we are told that we have two congruent triangles. So we're told that triangle ABE is congruent to triangle CDF. And since the triangles are congruent, corresponding sides and angles are congruent due to CPCTC. So these sides are congruent, they correspond, and these angles are congruent, they correspond. If I highlight these lines and this transversal, we see a letter Z. And in the corner of the Z's, we have congruent alternate interior angles. That means the lines forming them are parallel. If one pair of opposite sides is both congruent and parallel, the quadrilateral is a parallelogram. So here we have a parallelogram. One pair of opposite sides is both congruent and parallel. I'm going to draw a picture. Here's quadrilateral best. And it has diagonals that intersect at point E. Which statement would not be sufficient to prove it's a parallelogram? Answer choice 1. So there's a slight typo. It should be that they intersect at point D, and there should be a parallel symbol in between these two. It didn't print, sorry about that. So answer choice 1, BD is congruent to SD, and ED is congruent to TD. That does prove it's a parallelogram. If diagonals bisect each other, the quadrilateral is a parallelogram. So that does work. BE is congruent to ST, and ES is congruent to TB. That does work. If both pairs of opposite sides are both congruent and parallel, the quadrilateral is a parallelogram. Sorry, if both pairs of opposite sides are congruent, the quadrilateral is a parallelogram. Notice how both pairs of opposite sides are congruent. ES is congruent to TB, and BE is congruent to TS. That doesn't work. It needs to be one pair of opposite sides that is both congruent and parallel. It can't be this one congruent and this one parallel. That's not going to prove it's a parallelogram. So actually, I'll leave the markings because that is the one that's not sufficient. That is the correct answer choice. The last one is both pairs of opposite sides parallel, which does prove that we have a parallelogram. Here, angle B is 5x. Angle C is 2x plus 12. We know we have a parallelogram. Consecutive angles of a parallelogram are supplementary. So together, those two angles should sum to 180. And from here, I just need to take another second and solve for x. When I divide by 7 on both sides, I get x equals to 24. Be careful, it's asking you to plug in to find the number of degrees in angle D. So remember, opposite angles in a parallelogram are congruent. So if I do 5 times 24, that's 120, which makes angle D 120. We have a rectangle. We have diagonals. Remember, diagonals of a rectangle are congruent. And it also has the parallelogram properties. So diagonals also bisect each other. So not only are they congruent, but they also bisect each other. So instead of being like this, which is a regular parallelogram, since the diagonals are congruent, all the halves are going to be the same. AE is x plus 2. BD is 4x minus 16. And we need to find the whole length of AC. Well, diagonals are congruent, and this half is the same as this half, which is x plus 2. So 2x plus 2's is equal to the other diagonal, which is 4x minus 16. 2x plus 4 equals to 4x minus 16. And we get x is equal to 10. It is asking us to plug back in for the length of AC. 10 plus 2 is 12, times 2 is 24. We need to pick the statement that's going to prove that the quadrilateral is a parallelogram. Answer choice 1, angle 1 congruent to angle 6. And angle 9 congruent to angle 14. Those are vertical angles, and I don't think that justifies why we have a parallelogram. I'm not getting any information here. Angle 5 congruent to angle 10. And angle 6 congruent to angle 9. Well, these are two sets of alternate interior angles. And we know if alternate interior angles are congruent, we have parallel lines. Here's the letter Z for the blue angles. So that's showing this line and this line are parallel. Here's the alternate interior angles for the green angles. But look, the same two lines are parallel. So all this showed was that these two sets are parallel. Because those alternate interior angles, both pairs, are formed by the same lines. So, unfortunately, that's not enough. Angle 5 is congruent to angle 7. And angle 10 is congruent to angle 15. Well, angle 5 and angle 7 are corresponding angles. Top right, top right. So that shows the lines forming them are parallel. I'll make my parallel symbols nicer. 10 and 15 are alternate interior angles. So that means the lines forming them are parallel. But once again, it's the same two lines. So all this is showing is that these sides are parallel. We need both pairs of sides parallel. Or one pair that's both parallel and congruent. Angle 6 congruent to angle 9. So notice alternate interior angles. So these lines are parallel. Angle 9 and angle 11. These are corresponding angles, top right, top right. So the lines forming them are parallel. So that's the answer that we're looking for. That's the one that has angle relationships that show both pairs of opposite sides are parallel. We need to, in the next one, classify the parallelogram as a rhombus. So we already know it's a parallelogram. We need a rhombus property. True. In a regular parallelogram, the diagonals bisect each other. That's a parallelogram property, but the perpendicular part, having perpendicular diagonals, is a property specific to rhombuses. So that definitely does ensure that it's a rhombus if the diagonals are perpendicular, even though the bisector part is parallelograms. Diagonals bisect the angles. That absolutely is a rhombus property. Diagonals form four congruent isosceles right triangles. So since the diagonals are perpendicular, they do form right triangles, but the only other thing we know about the diagonals of a rhombus is that they bisect each other. That's a parallelogram property that applies. And that doesn't make isosceles triangles. These have different markings, and I don't know anything about this one. Different markings, don't know anything. Different markings, don't know anything. These could very well be scalene. I don't know. So that one doesn't work. And the reason it doesn't work is because that's a property of rectangles. Since rectangles have corner right angles, diagonals form right triangles as well. Since the diagonals are congruent in a rectangle, when they get bisected, each of the parts are the same because they're the same. So that when they get bisected, each half is the same as each other. So the isosceles right triangles is a property of rectangles. So 1 and 2 is the correct answer here. The isosceles part is what throws it off. Okay. This is a rectangle. 42 degrees. I know that the corner angle is 90. So let me figure out what the other piece needs to be. 90 minus 42 is 48. I also know that rectangles have parallelogram properties. So I know opposite sides are parallel. And when I have parallel lines cut by a transversal, alternate interior angles, are congruent to each other. Let's get the alternate interior angles from the other side as well. The more the better. And remember, the diagonals of a rectangle are congruent, and they're also bisected. So it does form isosceles triangles. And remember, if you have a triangle that has two equal sides by the base angle theorem, if it has two equal sides, the angles opposite those sides are congruent to each other. So if this is 42, this is 42. And that's really all I need. Because now, if I focus on this one triangle here, all angles of a triangle sum to 180. 42 plus 42 is 84. And if I do 180 minus 84, we get 96. So measure of angle 2 is 96 degrees. This question is challenging. It uses a lot of different rhombus properties. I think it uses all of the rhombus properties, in fact. So first, let's start with x, because x is on the sides, I guess, and because x comes first in the alphabet, so I want to go with x. So in a rhombus is equilateral. So that means consecutive sides are congruent because all the sides are congruent. So 8x minus 5 is equal to 3x plus 30. So we have 5x equals to 35. We have x is equal to 7. So if I plug in for SR, I have 8 times 7, that's 56, minus 5 is 51. So that's for SR. Now RT. RT is here. So there's Z on a piece of RT. And I know that a rhombus has the same properties as parallelograms. So the diagonals do bisect each other. But unfortunately, if I write 5z plus 5 over here and I set these equals to each other, although this is true, you're not going to get an answer because it's the same thing as each other. You're not going to be able to solve that equation. You're going to get infinite solutions. So rather, let's set, different markings. Let's set these equal to each other so we could find z. Then we can plug in to find this. So 3z is equal to 4z minus 8. Once again, diagonals of a rhombus bisect each other just like a parallelogram. So we have 8 is equal to z. Now let's plug in. So I'm going to plug in for ET. So 5 times 8 is 40, plus 5 is 45. So that's 45 as well. So together, this segment length is 90. RT has a segment length of 90. Angle TAS, that's represented with Y. What I'm going to need here is that diagonals of a rhombus are perpendicular. So over here, this is a right triangle, and I'm definitely going to need that. Now I can make an equation that says if I add all three of the angles together, it needs to make 180 degrees because all three angles of any triangle make 180. I'm going to get a little bit more space for this. So 90 plus 5y minus 2 plus 9y plus 8 equals to 180. Let me combine my like terms. Now let me solve my equation. I'm going to subtract 96 on both sides. And divide by 14. And my y value is 6. Now I'm going to plug in to find the measure of angle TAS, which is right here. 9 times 6 is 54, plus 8 is 62 degrees, because it's an angle measure. We're going to write a proof. We need to prove that ABCD is a rhombus. I only have 3 rhombus properties that are specific to rhombuses. I have equilateral, I have perpendicular diagonals, and I have diagonals bisect angles. That's the only 3 ways I can prove something's a rhombus, right? That's only 3 properties. I don't have diagonals here. I don't have AC, I don't have BD, I don't have diagonals. This is what we have to prove. We have our plan. We're going to try to prove it's equilateral. But remember, you don't have to prove that all sides are equal to show it's a rhombus. You can just show that 2 sides next to each other, consecutive sides, are congruent. Because since a rhombus is a parallelogram, opposite sides are congruent, which implies it's equilateral. So to make your life easier, let's go for showing 2 consecutive sides are congruent, which proves it's a rhombus, because that implies it's equilateral. Let's see what we have in our givens. So we already know that we have a parallelogram, so that makes our life easier because we don't first have to prove that this is a parallelogram. We know that BE is perpendicular to CED. Here's BE, here's CED. But wait, I don't know if this right angle is important or this right angle is important because I don't know what I'm focusing on here. Since I got the triangles in this area, I think the 2 sides of the rhombus, the 2 consecutive sides that I'm going to prove congruent, are the ones other sides of the triangles. Now I'm going to ask myself which triangles are those sides of. BC is a side of this large triangle. DC is a side of this large triangle. So these are the two triangles I want to focus on. Because if I could prove these two triangles congruent, then I can use CPCTC in order to get the sides I need to prove that I have a rhombus. These triangles are overlapping, so it's hard to see what's going on. So I'm going to draw them separately. And now, in the red triangle, the right angle that I want is the one that's in the red triangle. And the right angle that I want here with DF and BFC is the one that's in the green triangle. And they also tell us that CE is congruent to CF. That's hard to see here. It looks like I have to use addition, right, to get full sides. But if I transfer these markings to the separated triangles, I don't have to use addition. We already have full sides. They're just the short sides. I need some more information. The triangles are overlapping, so they're touching. There must be something shared. I see letter C is in both triangles. And that means angle C is shared between the red and the green triangle. Notice how they're both angle C. They're the same exact angle. That's reflexive property. We have angle side angle. Let's write this up. Write all your givens. Okay. Let's start with the right angles. I'm going to start with this one. Angle BEC. And now the other one. That is angle DFC. Here, DFC. Are right angles. And we know that because we had perpendicular lines. Perpendicular lines form right angles. Since we're going to be using ASA, ASA requires congruent angle pairs. So we do need to say that those right angles are congruent to each other. So angle BEC is congruent to angle DFC. And that's because all right angles are congruent. Moving on, we already have the side from the givens. So this was our angle, one of our angles, the right angles. The side that we're using was already provided in the givens, the S for ASA. So we just need to mention our shared angle, angle C. So I'm going to put that over here. And now we could CPCTC the sides that we want, BC and CD. And now we know it's a rhombus. So we can end our proof by saying ABCD is a rhombus. And here's our reason. A parallelogram with congruent consecutive sides is a rhombus. All done. Check out number 11. They tell us that ABCD is the square, so we know everything about it. It's a rhombus, it's a rectangle, it's a parallelogram, it's all of the above. And they tell us that AE is congruent to AF. I see triangles, that's information about the triangles, so that's real good. Prove triangle BAF is congruent to triangle DAE. Well, I see vertical angles, they're always congruent. And this is a square, so it's equilateral. So this side and this side are equal. So we have side angle side to prove the triangle's congruent. Let's write that up first, and then we can move on to part B. We're going to write it in the same statement reason chart. Square ABCD AE congruent to AF. Make that A better. So that's our side. AE congruent to AF. For side angle side, that's one of our sides. And then we have the vertical angles. Angle BAF congruent to angle DAE. Because intersecting lines form congruent vertical angles. And then we need our last side. So that was our A that we were using. So we have side and angle. Now we need our last side. DA is congruent to DA. And I'm going to put here all sides of a square are congruent. So now we have triangle. That was our last side, by the way. Triangle BAF congruent to triangle DAE due to side angle side. Next, we need to prove that angle CBF, that's this whole big angle over here, is congruent to angle CDE, this whole big angle over here. Well, since these two triangles are congruent, we can CPCTC this angle and this angle because they're corresponding angles. All angles of a square are congruent as well. They're all right angles, right? Because it's like a rectangle. So we're starting with congruent. There's another congruent piece. If we start with congruent and add congruent, we get congruent sums. So we can use the addition postulate, the addition property, whatever you want to call it, addition. Let's write out that addition. I'm just continuing my statement reason chart over here. I'm going to continue it with step number 5. Angle, what's this? FBA is congruent to angle ADE. And that's due to CPCTC. And we can say angle, what's this? CBA is congruent to angle CDA because all angles of a square are congruent. So now we can do our addition. Angle FBA plus angle CBA. And that gives us the angle that we want, angle CBF. And on the other side, we have angle ADE in purple plus angle CDA. That looks really messy. And that gives us this whole big angle CDE. the reason for step number 7, and I'll just draw arrows, is addition. And the reason for step number 8 is substitution. Substitution always follows addition or subtraction because we're replacing what we're adding or what we're subtracting with what it actually leaves us over with. This plus this is that. This plus this is the whole angle. This plus this is that. This plus this is the whole angle. We've achieved our goal. We have rectangle ABCD. The whole big quadrilateral is a rectangle. And we also know that angle ADG is congruent to angle BCG. And our goal is to prove that AE is congruent to BF. This one's going to be a little bit tricky because AF and BF are not sides of any triangles. But if I extend AE to AF, well, that's a side of this triangle. And if I extend BF to BE, that's a side of this triangle. But I'm going to have to probably do subtraction at the end in order to get just AE and BF. Because if I can get AF and BE, I'll have to subtract in order to make them smaller, right? Because AF is too long, I just need AE. And BF is too long, I just need BE. Sorry, BE is too long, I just need BF. I'm going to draw these two triangles separately as well. And I'm going to think about what I know about rectangles that's in these triangles. And I know that rectangles have right angles. I know that rectangles are parallelograms, so opposite sides are congruent. And from the givens, they already provided us with this angle and this angle. So we have angle side angle here. And since we have angle side angle, we could CPCTC, AF, and BE. And once we have AF, we'll just subtract to get AE. And once we have BE, we'll just subtract to get BF. Let's write this up. Rectangle ABCD, angle ADG, congruent to angle BCG. And that's given. And that's one of our angles for angle side angle. Let's do the right angles next. Angle A is congruent to angle B. And I'm just going to write here, all angles of a rectangle are congruent. It's true, right? That's how we knew it from knowing we have a rectangle. I could write angle A and angle B are right angles, and then all right angles are congruent. But why would I do that? This does it in one shot. Why do it if I don't need to, right? Let me do the side now. AD is congruent to BC. Opposite sides of a rectangle are congruent. Now I can say triangle ADF is congruent to triangle BCE, and that's due to angle side angle. And now I can say that AF is congruent to BE due to CPCDC. And now we just need to do our subtraction. So let's talk about what that subtraction is going to look like. You just get a little bit more space here. So we're starting with AF. Here's AF. And we need to arrive at AE. So this is the piece that needs to come off, EF. So I'm going to write that down over here. AE minus EF gives us, sorry, AF, that was the whole segment. Let me rewrite that. AF minus EF leaves us over with AE, which is what we want. And on the other side, here's BE. That's what we're starting with. We want to be left over with BF. So we need to take away FE or EF. And that leaves us over with what we want, which is BF. For our subtraction to work, we have to be starting with congruent. And AF and BE are congruent because we proved it in our proof. We also have to be subtracting congruent. But we never said that EF was congruent to EF, so we have to put that in our proof. And that's due to the reflexive property. And that's necessary in order to make our subtraction valid. So this is subtraction. And then we have our substitution. Because this minus this is that. AF, take away EF is AE. And this minus this is that. BE, take away EF is BE. So that leaves us over with what we need.